Hi students, let's look at this concept here, which is what we call the vector projection. So in this question here, we were told to find the projection vector of A onto B is given by this formula. So I think before we start, we must understand what is actually a projection vector. So a projection vector is essentially, say if I have A here and B here, all right, what I want a projection vector, this is A and this is B, project A to B. The vector that I want is actually this vector here. Take note, this is the projection vector. Yep. So this is the projection vector of A onto B. So of course, it goes without saying that actually the angle between A and B could be obtuse as well. So this is the other thing that we need to nail down when we derive this formula. So here, this case here, if this is A, this is B as such, then I know that the projection vector that I'm looking at is actually here. Okay, this guy here. So I need to find the vector here. So these are the two cases, okay? I know sometimes you can draw the other two cases, but actually they are all sum up to just these basic two cases here. So first thing is to understand that this is acute, that is over here is obtuse. Okay, so we need to consider both of these cases. And also the projection vector the direction when, let's say I project A to B, B is pointing this direction, right? But actually when I project A to B, I want to know what is the vector in the direction of sort of like the A, right? So the A, we are taking the direction of A instead of the B. So A here, when you project to B, this is the direction. You project the vector of A onto B, then what is the vector there? Okay, so to do this, we need a few concepts. Firstly, we need the length. So in other words, we need to use magic triangle, or rather the projection length of A onto B. All right, so firstly, we know that the length is just a magic triangle. Secondly, because the direction matters now, so we need to know the dot product. So we need to know the dot product well. Okay, so then thirdly, I think the most prominent one, the most important one is actually the application of a unit vector. Okay, so these are the three main concepts we need in order to derive the formula out. I think the projection length is rather trivial, right? If you already learned the magic triangle, you know that the projection length here, which is this length. So let's say the projection length of A onto B is just the dot product here. So just A dot B unit vector, right? Then similarly is a length. So I don't take into account the direction, all right? Right, so this will just be the projection length of A onto B. We're using A dot B, unit vector, because the angle they're looking at between A and B is this angle here. The acute angle is this guy here for this case, and this is this case here, right? So we are looking at A dot B and unit vector the adjacent side. Do not unit vector the hypo. So that is the first thing. Then secondly, what we need to understand is actually the more important thing is the dot product, or rather the unit vector. So I know that, say, unit vector, the idea of unit vector is for every one unit, okay, length parallel to B, I know that if I cut out one unit here, one unit, okay, one unit will correspond to B unit vector. So that's the definition of unit vector, meaning if you cut out one unit out, that would be the vector, all right, the vector which corresponds to one unit. So if I have a projection length of this, right, so now the question is, if I got the number of length, the projection length, which is mod A dot B unit vector units, right? Okay, so I can be sure that this will just be multiplied by the length itself. Okay, if it's 2, then you just multiply by 2 units, but this case is this unit here, so we get A dot B unit vector. Okay, so this is important. Now, because now the problem now is because so this is essentially parallel to B, all right, parallel to B. So you see that this is like parallel to B here. Okay, so but it's not taking the direction of A. So that is the main thing, which is what we need to use the third concept, which is the dot product. Okay, you realize that this case here, when this is obtuse, theta is obtuse, A dot B is actually a negative value. All right, then this case here, this is where A dot B is a positive value, because ASTC, cosine is positive when it's acute, right? So this is positive. So A dot B is mod A mod B cosine theta larger than 0. So you realize that the one which will give you negative is not mod A mod B because they are the length of these two vectors. The one which will give you negative is actually the cosine theta. So if cosine theta is in quadrant 2, is a negative value here, right? So this case here, since cosine theta is negative in Q2, then this is cosine, since cosine theta is positive in Q1. Okay, so this is the missing piece that we need, because this vector here is actually parallel to B. Okay, so when you realize that when theta is obtuse, okay, we write acute first. Okay, we know that what we want is theta is acute, the projection vector of A onto B is actually equals to this case here. What do we get? We need it to be positive, right? Because it's this vector here that we found, this over here, is this vector here. Okay, so it's this guy here. Okay, but since in this case, when theta is acute, right, we know that because we want to get the positive of this, and then what we can do is actually just remove the modulus. Okay, because we know that this guy here is positive. This guy is positive because this is positive since A dot B is positive. Okay, because of this guy, because the dot product. So this is the second concept we're talking about, because this dot product is positive. Now when theta is obtuse, then you will realize that the projection vector now will become negative mod A dot B modulus B. Okay, this is important. So essentially why we need it to be negative is because this vector here that we found is in the opposite direction of what the vector that is required. All right, so it's actually parallel in the same direction with B because we're using B here. So this guy, this is why we need to consider these two cases here. But fret not, because we could just apply a negative. So if we apply a negative, it will be the opposite direction, which is the orange, which is this direction that we want, which is like parallel to A. Okay, so this case here, what we need to understand is when theta is obtuse, we know that A dot B is negative, right? So essentially, actually what we can do, in order to make this positive, there are a few ways of looking at it. Because this has to be positive, so in other words, we have a negative A dot B unit vector. Okay, for this, you open up the modulus, is this guy, right? So this is mod B unit vector, since A dot B is less than 0. Okay, so once this is essentially, this is because this is less than 0. To mod meaning I need to make it positive. So it just happens that we can put a negative here in front to make this positive. Open up the modulus, because opening up modulus will mean that we need to pick one, right? We need to pick one. So similar with this guy here, we need to pick whether we need to take this or negative A dot B. Okay, but this guy is positive, so I pick this. This is negative. For this case here, A dot B is negative, then is A dot B less than 0. This is positive. Okay, so I pick this guy. So after picking this guy, you realize that even for obtuse, negative will be positive. This guy here is actually the same vector equation. Do you see that? So hence, for theta, for all theta, right, acute or obtuse, you will get this is your projection vector. Okay, so that's it. You just combine 1 and 2 for acute and obtuse. You realize that both yield the same result here. I think the main thing is to understand that there are three concepts at play. One is the unit vector, which is the unit vector then the magic triangle, which is the projection length, then the dot product. Okay, the dot product give rise, because when you open up the modulus, is much easier for us using the dot product. So we take A dot B unit vector multiplied by unit vector of B. Okay, because this would just decide whether we take the positive direction or the negative direction. Okay, so that's how we derive this projection vector here. If you have any questions or comments, please do let us know, and I'll see you in the next question.